Welcome to the Robotics and Digital Media Experience. Developed by Discovery World's Experience team, this customized program was created for freshman engineering students at the University of Wisconsin-Milwaukee. My fellow students and I built robots inspired by nature. We also learned how to write scripts, conduct interviews, and communicate scientific topics. This program encourages innovation and experimentation by bringing together robotics with biomimicry, creativity, and digital media production. As students and tomorrow's engineers, we discover, innovate, and lead. This is Innovation House, the robotics and digital media podcast produced by Discovery World and sponsored by the Forte program. Forte means fostering opportunity for tomorrow's engineers. We are tomorrow's engineers, preparing at UWM Milwaukee. Hello, I'm Amanda. Today, we're going to explore biomimicry and robotics. And we have an insightful interview with Lisa Winders, a 2011 graduate of UWM who trained to become an engineer. But first, we'd like to tell you why we love engineering.
My name is Kelvin Brousseau, and I'm a future mechanical engineer.
My name is Mason, and I'm studying materials engineering at UWM.
My name is Amanda Field, and I'm an industrial engineer specializing in logistics and distribution.
My name is Noah, and I am a future electrical engineer.
I chose computer science because I've always loved video games.
Because I love working with robots.
Because many companies need help with automation processes.
Because I enjoy being a leader.
I want to explore the language of computers and video games.
It amazes me that people can create games and websites with code. Just strings of words and numbers on a computer screen.
I really want to use my creativity to make big companies more efficient.
I like the idea of using fully autonomous robots to assist during surgery.
The thought of creating new materials is thrilling.
My father, uncle, and grandfather are all engineers.
My grandfather is a mechanical engineer.
I think that becoming an engineer was almost written into my DNA.
Green transportation is a great example of innovative engineering.
If all cars were self-driving, the roads would be much safer.
To me, the pyramids of Giza are an example of extremely innovative engineering. Simple tools and human ingenuity can lead to brilliant outcomes.
I would love to create advanced computer systems for spacecraft.
I would love to create a new material, perhaps something that could be used in a lens to enhance the human eye.
If I could invent one thing, it would be to invent an airplane that runs on alternative fuels. This would help clean the environment and cut down on the cost of air travel.
Whatever I invent or create, I know that I will want it to have a positive effect on the people around me.
Nature consists of incredibly complex systems that we almost never notice.
It has such an astounding underlying complexity.
I'm fascinated by the way large organisms like trees or humans transmit and process information.
New forms of technology are similar in this way. If a piece of technology is really well designed, then all of the complicated parts are almost invisible.
My name is Amanda, and I love engineering.
My name is Mason, and that's why I love engineering.
The team here at Discovery World challenged us to design and build robots inspired by plants. This kind of design and engineering is called biomimicry. It's a way of exploring the natural world to solve engineering challenges in the built world. We chose our plants, we watched our plants in action, and we discovered that plants are a great inspiration for robots.
How can a robot grow without growing? To find the answer, we looked at flowers. Hello, my name is Troy, and I am a future mechanical engineer at UWM.
And my name is John, and I am a future computer engineer at UWM.
Our robot is inspired by the tulip plant, a common spring flower found all over the world. Tulips are pretty and come in a variety of colors.
What makes the tulip plant interesting is that the plant can extend itself towards sunlight by stretching and bending without undergoing cellular division. In other words, the plant can grow without actually growing. One side of the stem elongates in response to sunlight.
Our robot mimics the elongation movement of the tulip plant. There are two pulley systems, here and here, that move either side of the stem up and down. The up and down motion angles the flower. of our robot to face the light source. And here are the light sensors that detect the light source.
This is our light source. It represents the sun. Our robot will follow the light source as we move it. All right, now we're going to do a demo.
We've turned the lights off for the demo, and here we go.
Wow, that was pretty cool.
This was a great experience, but we did have some challenges. For example, we had to decide how to accurately mimic the movement of the tulip.
The real tulip is capable of moving in any direction in 3 dimensions. We found that this kind of movement was difficult for us to replicate.
We overcame this challenge by simplifying our design. We built an actuator here. The stem elongates on one side or the other in response to light, which moves the robot flower here.
This was a great experience because we learned that plants are amazing, and we learned how to work together to overcome engineering challenges.
And that's why we love engineering.
What is biomimicry? How can we look to nature to build a better world?
Hi, my name is Amanda. This is Grant. We are future engineers.
Amanda and I created a robot inspired by the common bean plant.
The common bean plant is native to the Americas, but it grows almost everywhere in the world. The bean plant is interesting because its leaves follow light, which allows for the plant to absorb as much light as possible.
The bean plant detects and reacts to different wavelengths of light. Blue light triggers growth, and red light triggers photosynthesis. The large leaves of the bean plant follow the sun as it moves across the sky.
The robot will grow and follow the light depending on the color it detects. When the robot detects blue light, it will grow up. When it detects red light, it will angle its leaf towards the light source. This is the brain of the robot. It has all the circuitry and also runs the program that controls the robot. These are the servos that make the robot move. A servo is, essentially, a programmable motor.
This is the pulley system that we designed to transfer force from the servo to the robot. Here's the light sensor that we programmed to detect red and blue light.
Enough talking, let's see the bean plant robot at work. Here we have a red and blue light source. Grant is going to turn the robot on, and I will change the light color. The robot will move according to the light frequency.
And now let's do the demo.
We're going to take this light source, turn it on to blue light, and then our bean plant will move upwards. Very slowly, because bean plants grow very slowly.
And we turn the red light on. The leaves at the top will rotate due to them following the sun. One challenge we had was figuring out how to make the light sensor respond to blue and red light.
We solved this problem by figuring out the proper light values and creating the right program to run the light sensor.
This is a great experience for me. It's taught me that nature is a really good source of inspiration for engineering solutions. Nature creates incredibly clever solutions to fundamental problems. In this case, how does a plant get as much sunlight as possible? That's a powerful tool we can use going forward.
And I love learning to convey fascinating scientific topics in an interesting way.
How do you turn a plant into a robot? Hi, my name's Noah, and I'm studying electrical engineering at UWM.
Hello, my name is Alan, and I'm studying industrial engineering.
Our robot is modeled after the Venus flytrap. The plant is native to North and South Carolina and is found in the damp, nutrient-poor soil of bogs and swamps. It is interesting because it is carnivorous.
Because the soil that it lives in lacks nutrients, the plant relies on nutrients from insects and other small organisms. The Venus flytrap has a leaf that resembles a jaw. On that leaf are tiny hair triggers.
If a bug lands on the leaf and triggers 2 of the sensors within 20 seconds, the jaw snaps shut, trapping the bug. The Venus flytrap then secretes enzymes that digest its prey.
Our robot is designed to mimic the trap mechanism of the Venus flytrap. This is the brain of the robot. These are the gears, and these are the 2 halves of the trap that close in the insect. These are the pressure sensors that communicate to the brain to close the jaw when they have been touched.
All right, let's eat some bugs.
All right, it worked. One big challenge was programming the pressure sensors to react in the same way as the trigger hairs of the Venus flytrap. Getting the timing right was a process. Neither of us had ever programmed a robot before. And we overcame that challenge with the help of the educators here at the Discovery World.
This was a great experience because we got to build a robot and explore the principles of biomimicry. We both really like to make things, and this hands-on experience was an awesome opportunity. And that's how you turn a plant into a robot.
Recently, we interviewed Lisa Winders, a mechanical engineer and 2011 graduate of UWM. She shared her work as an engineer and a cost analyst at Johnson Controls with us. Our guest today is a mechanical engineer who graduated from UWM in 2011.
She works at Johnson Controls as a cost analyst, and she's earning an MBA at Marquette.
Lisa Winders.
Thanks for having me here.
Lisa, what led you to pursue engineering?
Well, I've always had a love for math and science and a natural curiosity for how things worked, so when I was introduced to an advanced science and engineering course in high school, it just seemed like the right fit.
What were the most challenging courses you took at UWM, and how did you get through them?
For me, the most challenging courses were my materials science courses. It's always been easier for me to learn when I can visualize something tangible, but I got through them by going to my professor's office hours and seeking help from my fellow classmates.
As you look back at UWM, what was one of the most rewarding experiences you had?
I would say it would either be my senior design or my mechatronics class. At that point, we were able to pull everything that we'd learned over the years and translate it into a tangible product for a real company, and I felt a great pride in doing that.
What advice would you give to new engineering students?
I would say, although at times it doesn't seem like it, but your professors are always there to encourage and support you and help you when you have questions.
How did you get involved with Johnson Controls?
Well, I was introduced to the company at a career fair, and after doing some research and finding that my values aligned with theirs, I applied for an internship, and I've been with them ever since.
Tell us about your work at Johnson Controls.
That's an interesting question. I'm actually transitioning between jobs right now. I started with the company as an advanced manufacturing engineer, taking our lithium-ion batteries from prototype to production and speccing the equipment behind the assembly. And now I'm currently moving into a new role as a cost analyst, where I build up our product cost and drive our engineering teams to meet our financial targets.
Lisa, what is a lithium-ion battery?
Well, it's a rechargeable battery that uses lithium ions. There's 2 electrodes, positive and negative, and the ions pass back and forth during charge and discharge to provide power.
What is the future for lithium-ion batteries?
Well, the future right now is in our micro-hybrid battery system that we're currently developing. It's to be used in conjunction with your lead-acid battery, so you don't have to change the vehicle architecture, but it still provides 15 to 20% fuel economy savings.
What's it like working at Johnson Controls?
Well, it's been great. The company is very open, the culture is very caring, and we're really focused on innovation and new products.
What inspired you to pursue an MBA, and how does that reflect your future career goals?
Well, along with my natural curiosity, some of that comes with how a business operates. I wanted to learn more, not just about the development side, but the work that goes behind it. So that's why I started my MBA. And then for future career goals, I'm hoping to explore some of those other career opportunities within our company.
What are the new and next emerging careers in engineering?
Well, from my perspective, I would say they would be careers in either renewable energy sources or automation.
What made you a good candidate for a JCI internship?
Well, I worked hard in my courses, but aside from that, I took on a handful of extracurriculars, from being a part of our funds appropriation committee for Student Senate to 2 different research assistantships, one with the School of Engineering and one with our physics department.
Well, Lisa, thanks for stopping by.
Yep, thank you.
Thanks for being here.
Well, thanks for having me.
And that's our story. We'd like to thank Lisa Winders for joining us. We'd also like to thank Discovery World and UWM's Forte program for making all of this happen. At Discovery World, we explored robotics, digital media production, and communication skills. We tinkered with ideas like biomimicry and turned those new ideas into something real. And that's what engineering is all about. This was a great opportunity to discover, innovate, and lead.